All right, thank you everybody for coming today to our traffic flow webinars. Today we have our first PhD student guest in our webinar. She'll be talking about variable speed limit. Um, if you could please mute your mic because I hear a bit of feedback going on. All right, today we have Irene Martinez. She obtained her undergrad degrees from UPC Barcelona Tech, and now she is a PhD candidate at the University of California, Irvine, working under the supervision of Professor Wenlong Jin. She's interested in traffic flow modeling and the mitigation of traffic congestion in the area of autonomous, connected, and shared mobility. Her research work has been published in Transportation Research Part B and C, and she has presented at the ISTTT Symposium in 2019 and in the TRB conference as well. And she has also received numerous awards, even though she's in very early stages of her career. So Irene, thanks again for coming and agreeing to give this webinar, and the floor is all yours.
Thank you very much for the nice presentation, for the opportunity. I'm very happy to be here, and let's start. So as you know, traffic congestion increases carbon emissions, air pollution, car crashes, on top of the increased travel time for users. So this congestion, when it's recurrent, it usually arises because there's an imbalance between demand and supply. And since we cannot increase supply infinitely and being adaptive to the demand all the time, what we need to do to prevent this traffic congestion is to control the demand. So during my PhD, I'm exploring different types of demand management strategies. For example, congestion pricing or fleet sizing for shared mobility systems at the more network or city level, and also more traditional types of controls, such as variable speed limit at the freeway level to alleviate severe congestion. So after some presentations at the network level modeling of traffic flow in this webinar series, now I'm going back to the more traditional link fundamental diagram and the LWR model. So in this presentation, I will talk about traffic flow at local bottlenecks and how to design properly the location of the variable speed limits in order to prevent the phenomenon called capacity drop. Bottlenecks are changes in the geometry of the road that limit the capacity, and they can be found everywhere, from a lane reduction, a merge, an increase in slope, and even a tunnel. These bottlenecks are just like funnels. And for a visual representation, I've chosen the lane drop bottleneck, which is a clear reduction in capacity, right? So we have an example here with an upstream capacity C1 and a downstream capacity C2, or bottleneck capacity, which is lower. And these bottlenecks are just like funnels. So if the demand to the bottleneck doesn't exceed the capacity of the bottleneck, the maximum flow can be observed, the C2. However, when queues start to build up, this phenomenon called capacity drop arises, and the outflow is much lower. It has been reported empirically that this reduction is between 5 and 20%. This increases travel times a lot, and then we want to prevent it. To do so, what we need to do is to control the demand to the bottleneck by reducing it, right? The most traditional way of doing so in the United States, at least, is using RAM metering. So you are controlling the inflow to the freeway. However, not all bottlenecks, as I said, are merges. So we need to rely on other controls. And in general, also, RAM metering is also used in, or proposed to be used with variable speed limits altogether to be more efficient. So what's the idea behind this mainline control with variable speed limits? You have presumably an excess of demand that would generate a very severe queue. And what we do is to generate an upstream region with a lower speed, which reduces the flow. into the bottleneck. And this artificial queue is supposed to let vehicles accelerate away from this zone and pass through the bottleneck without stopping and without causing the capacity drop. However, most of the work that's done regarding the variable speed limits is centered on which speed limit we should impose depending on the traffic conditions, so measuring the density and so on. But a very important question also is where should we locate these variable speed limits? As I will show in a couple of slides, there have been some conjectures on how this location should be chosen, but there is no systematic study about it. So I started having some curiosity about this. Sorry. During my master thesis, where I did some simulations. And here we can see how if the control is too close to the bottleneck in your left-hand side, the vehicles will still slow down inside the bottleneck, causing the capacity drop. However, if the design of the variable speed limit zone is in an efficient position, like in the right-hand side, the vehicles will reach their destination faster. And that made me look into the literature and see whether people are really discussing about it. And the only work that I could find explicitly discussing the effect of the location was a work by Tipakianaki. Her type of control was traffic light control, not variable speed limits. But they explicitly, among other things, studied the effect of the location on the travel time savings. The work was done based on simulations in the AIMSOM software, with AIMSOM software. And here we can see a figure, and we will look into the black line where the distance between the control and the bottleneck is depicted, and in the y-axis we have the average vehicle delay. We can see when we increase the distance for a while, this average delay reduces, but there is a point where there's no extra benefit on moving the control further upstream. This is very important because since we are generating an artificial queue in an upstream location, this queue could block other off-ramps or on-ramps. So we don't want to put it too far away from the bottleneck. So as I said, there is a large literature, and I won't go over it on variable speed limits and its design. But let's see about this conjecture that I was talking about. So it is believed there's a distance needed between the speed limit zone and the bottleneck that should allow vehicles to reach a certain speed before entering the bottleneck. This speed can be the free flow speed or the critical speed, which is the speed at which the capacity is observed. But these speeds are the same for the assumption of the triangular fundamental diagram. So if we plug in some numbers, we can see that for a given free flow speed and a given acceleration and the range of speed limits, this required distance from kinematic equations is very large. In fact, the lower the speed limit, the longer this acceleration distance is. And this is not very good for the reasons that I was saying, that especially in motorways close to the cities, you have many on-ramps and off-ramps that are very close together. So this distance might not be reasonable, because if you have on-ramps or off-ramps in between the control area and the bottleneck area, you will need to implement ramp metering as well and need to develop a combined control strategy, right? So these conjectures have all been done without any systematic study, and there is no discussion whether this distance is either sufficient or necessary. And today I will present an analytical formulation to obtain this optimal distance. This optimal definition is based on the assumption that we need to put the control as close as possible to the bottleneck, but at the same time prevent the capacity drop. So to do so, we need a model that captures the capacity drop. And I will be using the LWR model with bounded acceleration. I won't go over the details of the model, but it has been shown in published work by my advisor, Professor Wenlong Jin, that just considering capacity reduction and inhomogeneous road and the bounded acceleration with this first order model, it's enough to reproduce the capacity drop. In fact, the drop capacity, the C3 value, can be endogenously obtained from the parameters like the geometry of the road, the variable speed, the fundamental diagram parameters, and the acceleration or bounded acceleration model. So let's go back to our bottleneck with a reduction in lane. We have modeled this lane reduction by a piecewise linear number of lanes, which generates an inhomogeneity in the fundamental diagram. And also when we introduce this speed limit zone upstream of the bottleneck, we are generating an additional inhomogeneity. So the speed limit now is location dependent as well. And so the speed density relationship is location dependent and has two different inhomogenities. So we have a very big transition zone between the end of the bottleneck, the end of the control, and the end of the bottleneck. The three main variables that I'll be talking today are the speed limit, the end of the control or distance between the speed limit zone and the bottleneck, L, and the outflow from the control, CU. So the first question should be, what type of speed limit should we impose? In this work, I'm assuming open loop control. So there's no feedback. I assume that the demand is high enough to generate the capacity drop if we don't control it. And we won't be changing the speed limit. So for a given speed limit, I design, let's say, an optimal location. So we are interested in having speed limits that allow outflow between the drop capacity and the bottleneck capacity. Because if we have higher speed limits than that, the outflow is not controlled enough and there's still an excess of demand to the bottleneck. If we would put lower speed limits than U3, which is the speed limit associated to the drop capacity, we would have a lower outflow than the drop capacity, which is, there's no point in doing so, because we would be better off having just the capacity drop phenomenon form. So the model that I'll be using is equivalent to this two-phase model. The idea is that traffic can be in two different states, either the bounded acceleration state or the equilibrium state. If the traffic is in the bounded acceleration state, its speed is determined by the maximum acceleration of the vehicles. And this speed would be lower than the equilibrium speed, which is the speed density relationship from the fundamental diagram. However, if the traffic is in equilibrium state, the speed is defined by the fundamental diagram, and the acceleration is lower than the bounded acceleration or maximum acceleration. This two-phase model has been shown to be equivalent to the LWR model with bounded acceleration recently, and I'll be using more like this bounded acceleration LWR model formulation. But I will be focusing on stationary states. So there is no time dependency. Both speed, density, acceleration are time independent. And I will refer to this as BASS for the bounded acceleration stationary state and ESS for equilibrium stationary state. As you know, when there's a stationary state and there's no time dependency on any variables, the flow is also constant. So here we have the definition of BASS and ESS. And of course, because the equilibrium stationary state is defined by the fundamental diagram, we can have both a congested equilibrium state or a non-congested equilibrium state. So we define globally two different types of stationary states. And for both cases, for the congested stationary state and the uncongested stationary state, the variable speed limit zone is, let's say, in the congested equilibrium state because there's a Q, and the speed is determined by the speed limit. But there's a Q, so there's enough demand. But the difference is in this transition zone, the acceleration zone plus the bottleneck zone. So in the congested state where capacity drop will arise, the whole stretch is in congested equilibrium stationary state. When the vehicles are in an uncongested stationary state, when they exit the variable speed limit zone, they are able to accelerate freely at their maximum acceleration in a bounded acceleration stationary state until they reach the free flow speed. And then uncongested equilibrium stationary state is observed. Downstream of the bottleneck, in any case, we will have this bounded acceleration stationary state. So in a little bit more visually, here we have the speed profiles. We see that where there's an equilibrium stationary state in an homogeneous region, so zone 1, the speed profile is constant. But in the bottleneck, the speed profile increases in a convex way. And when we are in the PSS state, the speed increases, but in a concave way. When we look at the uncongested stationary state, the speed profile is all concave, and the state is in bounded acceleration state until the free flow speed is reached. So just by a quick look at these graphs, we can see that for the same initial speed, the vehicles in an uncongested stationary state reach higher speeds earlier because the acceleration is faster. So to discuss which stationary states can arise, depending on the different conditions, we will go over shortly on the admissible condition of each state. Basically, the congested stationary state can arise when the acceleration is lower than the maximum, or equivalently, the flow is lower than the drop capacity. For the uncongested stationary state, where the capacity drop can be prevented, the bounded acceleration state is observed downstream of the VSL zone, right? So the speed must be lower than the equilibrium speed, which can be reformulated with a little bit of algebra as a minimum speed. So the speed in the uncongested region, uncongested state must be at least this minimum speed, which is depicted here. We see that outside of the bottleneck, this minimum speed is constant. And in particular, it is the speed limit in the acceleration area and so-called target speed V2 downstream of the bottleneck. So when is this uncongested stationary state feasible? Let's say that we have a variable speed limit zone that ends at a given location, x equals minus L. Here the zone is in blue. So we have this bounded acceleration stationary state profile, but it's not feasible because it doesn't satisfy the condition on the minimum speed. So what we can do is move this control further upstream, having a bounded acceleration state that is feasible. We can move this speed profile back and forth and see that the condition is actually a condition on the speed at the end of the bottleneck. So this location basically needs to be enough to guarantee that the V2 speed is reached at the end of the bottleneck. So what is V2? It's a great question. It's basically the speed on the congested branch of the downstream fundamental diagram here in green. So if we lower the speed limit, this V2 is lower. When we increase the speed limit, this V2 increases up to the maximum reasonable speed, which is the free flow speed. So Basically, for the maximum reasonable speed limit U2, we have a target speed of the free flow speed. This is more or less consistent with the conjectures in the literature. However, this target speed is not at the beginning of the bottleneck, but at the end of the bottleneck. So we can look at the control of the speed limit zone closer to the bottleneck than it was thought until now. So now that we have the admissible conditions, we can, for any given geometry and fundamental diagram, we can know what would be the solution of the stationary state. And I have, I present here a very simple representation tool where the X and Y axis represent the two design parameters of the variable speed limit control. And for any given speed limit in the Y axis, you can see what is the condition on the location, right? So we said that to have an uncongested stationary state, the condition is that the distance between the bottleneck and the control is larger than this value. So below of this blue line, the states can be in the uncongested state, and the capacity drop can be prevented as long as the speed limit is lower than U2. So the blue region here is actually not of interest. Even if we have an uncongested stationary state, the flow is lower than the drop capacity. And the green region is the interesting one. The higher the speed limit, of course, the larger the flow would be. And the red region is the region where the capacity drop would be observed. So with all these analyses, it's very easy to define what's the optimal location of the variable speed limits. Basically, it's the minimum distance that I already said that allows to observe or prevent, the capacity drop. So observe the control flow. And from the figure from a couple of slides ago, we see that the condition is that the speed V2 is reached. So basically, we have an expression for this L bar U, and it's something like that. I won't go over the details, but here we can see that this optimal location depends on the speed limit, on the geometry of the road, on the shockwave speed, and also the bounded acceleration. In fact, contrary to general belief, the more that we increase the speed limit, the longer distances we require. So if we reduce the speed, we reduce the optimal distance. And if the speed limit is low enough, lower than the U3 speed, which is associated to the drop capacity, the location is totally irrelevant. So we can put the control just upstream of the bottleneck. This is not of interest, as I said, for open loop control, but if the capacity drop has already been observed or is formed, we can use this strategy to eliminate the queues. So in summary, if we design the variable speed limit location for the maximum reasonable speed limit, it will work for any other speed. And here I have a short sensitivity analysis for different types of bottlenecks with different number of lanes, from 5 to 4 lanes in green, and you can see the others. Here we show how by reducing the speed limit in the x-axis as a function of the maximum reasonable speed limit U2, the flow decreases. Also, the target speed decreases, as we said, but it increases more significantly for smaller or freeways with less number of lanes. If we look at the optimal location, it's the freeways with more number of lanes that decrease faster. The optimal location decreases faster with the speed limit. In fact, this reduction of optimal location is at least cubically with the speed limit. And here, all these data points represent feasible speed limits between U3 and U2. So for the optimal location in the most right-hand side graph, we can see that for many other speed limits that are not lower than the U3 value, we can still put the control just upstream of the bottleneck. So the distance can be 0. Now I present an example from an existing freeway, and the data has been published, so I didn't collect it. It's on the westbound Gardiner Expressway in Toronto, where there's a lane drop bottleneck, and the parameters have been calibrated. And here on the left-hand side, we see different colors, speeds at different locations. So we see that the speed changes over the distance, but the flow rate is more or less constant. That means that it's a stationary state. And because it's downstream of the bottleneck, it's a bounded acceleration stationary state. We take the average of all these data points and can estimate what is the bounded acceleration profile downstream of the bottleneck. We can estimate the acceleration and also the bottleneck length as 0. And from that, we can further estimate what is the equilibrium stationary state or congested equilibrium stationary state inside the bottleneck when there's no control. Then for this calibration, we get these parameters, and we can calculate the target speed and optimal location for any given speed limit. I have chosen something that is slightly smaller than the maximum reasonable speed limit. And here we can see how it would look like. So the distance is around 300 meters, relatively short. And in gray, I have depicted what is the distance required to reach the free flow speed. So if we would place the variable speed limit zone in the location with our traditional thinking that the vehicles need to reach the free flow speed before entering the bottleneck, it would be located here. As you can see, there's a big difference, around 900 meters, and we can use all this space to have queues and prevent the blockage of other on-ramps and off-ramps upstream. Okay, so all what I have been talking today is about lane drop bottlenecks, but of course this can be extended to any other type of bottlenecks. Now I will be going very shortly over sag and tunnel bottlenecks. Basically, we do something similar. We model a reduced capacity. Why is there a reduced capacity in this type of bottlenecks? Basically, when you are, let's think in a car following state, if you're following your leader, the distance that you're keeping with your leader for a certain speed is larger in a sag or in a in a tunnel in comparison to other locations. So this larger gap means that for a given speed, the flow rate is smaller. This can be modeled with an increase in time gap over a certain stretch. And this has been already proposed in the past. And basically what you're doing by increasing this time gap, we are reducing the congested branch, lowering the congested branch of the fundamental diagram, generating a reduced capacity. And we would proceed in the same way. We define the global stationary states. We have similar conditions to obtain the uncongested stationary state and prevent the capacity drop. There is a minimum speed, and there is a target speed V2, and then we have the optimal location. I just put the equations here in case anybody is curious or interested. So basically, to wrap up, what we saw today, or what I presented today, is I considered an open loop variable speed limit control. So there's no change in speed over time. And also, I assume that the speed limit is imposed and everybody fulfills it. So there's no analysis on on the compliance rate. That would be further research. And based on the bounded acceleration LWR model, we have defined two different global stationary states, and we have discussed the admissible conditions for those to arise. We have seen that to avoid the capacity drop, a bounded acceleration stationary state needs to be observed downstream of the control zone. And for a given speed limit, we can calculate a target speed and then a minimum distance between the control and the bottleneck to prevent this capacity drop. We have also presented a very simple representations tool to obtain the solution of the stationary states for a given speed limit and location. And basically, we have defined and solved the optimal location problem, both for lane drop bottlenecks, channel and sag bottlenecks. So what does that mean for the design of the optimal location of the speed limit control? So in comparison to what it was taught in the literature, there is a distance between the control and the bottleneck that is needed, but this distance can be zero in some cases because it depends on many variables. The vehicles don't need to reach the free flow speed before entering the bottleneck, but they can continue accelerating inside the bottleneck and even downstream of it. And finally, even if it's counterintuitive, it's also beneficial that higher speed limits would lead to longer required distances. So we can design from an engineering point of view the location for the maximum feasible speed limit, and we would be on the safe side of the design. Of course, this all can be applied. What I discussed today is imagining that the speed limits are applied with variable method sense, but it can be done in a connected environment situation where we have vehicle to infrastructure communication, thinking on the future. And this would help us to have a better measurements, because we won't have like this all what I presented today is open loop, but we can extend this for closed loop, of course. And if we have the measurement of connected vehicles, we would be able to measure the speed at different locations of the road. So it would be easier to estimate in which state we are or towards which stationary state we are going, and adapt the controller in a better way than if we have just a occupancy detector, loop detector in a single point. When we have connected vehicles, each vehicle can have its own control design. So the speed and the location can be designed individually. And of course, that would allow us to study the compliance rate if we look at the different market penetration rates of connected vehicles that follow the speed limits. So why I think that this study is important to further develop closed loop strategies is explained here briefly. So assume that we have already our capacity drop formed. We are observing a stationary state like the red line here, dashed, by the way. So to reduce this or to eliminate this capacity drop and eliminate the queues, we put a speed limit that is lower than the that allows a lower flow than the drop capacity. This speed limit from the theory can be put just upstream of the bottleneck, and then the vehicles accelerate in a bounded acceleration state. And when the queues are eliminated, you can slowly increase the speed limit by moving it further upstream, and then have always the speed control at the optimal location. And sorry, until we observe the dropped capacity flow, the C2 flow. And in this way, we were able to recover the maximum flow of the freeway in a more efficient way, because all the strategy and the controls are very close to the bottom. And that's it. Thank you very much. And I'm happy to answer any questions.
Thank you, Irene, for such a good presentation. I think in the chat we have a question or two. Let me read it for you from
Okay.
Ramchandra. Irene, thanks for the nice presentation. I have a couple questions. First, why the LWR model was used?
That's a very good question. So basically, because I said we need a model to reproduce a capacity drop, and this is a very simple model which doesn't require us to go into the vehicle-to-vehicle interactions. It's probably the simplest model to reproduce the capacity drop and analyze this first-order stationary state. Of course, I'm very interested in looking whether this type of control and design of location would apply for any other model, any car following model, any software simulation model. All this is still an open question, but I'm really, really looking forward to see whether this applies to any any model.
All right,
Did that
and the
answer the
second
question?
question he had is any implications on safety by control of variable speed limit?
Oh, so I didn't talk about that here. So the speed limits imposed are very, very low. And of course, we cannot, if we are having a freeway that everybody's traveling at very large speeds, we cannot just in a section put a very low speed limit. Traditionally, in the literature, what many researchers do is to put subsequent gantries by lowering the speed limit little by little, and then until the certain speed is reached. So there's no problem with safety. But of course, with the connected world, each vehicle would have its own profile, and it should be safe.
Right. So just a reminder, you could unmute yourselves and ask a question if you want, or
Yeah,
in the
sure.
chat box. I was wondering about the acceleration you have. So are you assuming constant acceleration, or is it a function of the speed?
It's constant, but if we would consider any other function of the speed, as long as as long as the acceleration decreases with increasing speed, which is reasonable, the bounded acceleration state observed would still be this concave function, and then it would still apply all the analysis. We just need to focus on the target speed. And with that and the bounded acceleration model, we can estimate either analytically with a constant bounded acceleration or numerically solving an ODE problem the optimal location.
And do you assume the same acceleration for all vehicles?
So this can, of course, be relaxed. There is a paper by WADA that actually is the one that we presented in ISTTT last summer, where the heterogeneity in the bounded acceleration was considered to analyze the capacity drop. And of course, when you have different bounded accelerations, the vehicles that have a lower acceleration acting as moving bottlenecks. So these ones would determine what is the drop capacity in a sense. And we should design this type of control for this lower acceleration. But I haven't tested with whether with this vehicle heterogeneity, this type of control should be designed exactly like this, or there should be other things that need to be considered, like the variance among acceleration or so. But it's a future extension.
So I have a question on what to be considered, because you just mentioned that when first, nice presentation as always. Here. That, like in the practice, like you have gantries that speeds are decreasing, is not the case that the main factor here, or not the main, but then one of the important factors here is that the deceleration is also unbounded.
Yes.
And if that can be extended, and what's your thoughts?
Yes, so here the deceleration is unbounded. If we would do, let's say, a simulation model, I would consider an unbounded deceleration right now. But again, this is an analytical study, and the whole upstream region is VSL. So I'm not modeling, or I'm not discussing at all on the deceleration from the, let's say, from the regular conditions to the variable speed limit zone. This deceleration is not analyzed or considered in this paper. It would be equivalent to assume an unbounded deceleration. This should be relaxed to have a more realistic model, of course, but this deceleration doesn't affect on the downstream part, right? The bounded acceleration states, and all these states are accelerating or constant speed. So the bounded or unbounded deceleration won't affect this analysis. It might affect the upstream part, but not this part of the analysis. Does that answer the question?
Yes.
Felipe?
So, Irene, typically one would think that you would have to accelerate till free flow speed, but you showed that actually you don't need that, right?
No. So only if the speed limit is the maximum one, so associated to the bottleneck capacity, then you should reach the free flow speed, but at the end of the bottleneck, not before entering.
Do you have a figure to illustrate that?
Let me look for the figure. Why?
Sorry for the trouble.
No, it's okay.
Because I think that's an interesting result.
It is. It's counterintuitive.
They design ramp meters, the ramp length, so the vehicles can reach free flow speed when they enter, etc.
So So here, like here we see the minimum speed. I'm showing the slide, right?
Yeah.
Okay. I'm showing the minimum speed in blue, and because this function is concave and it's constant outside of the bottleneck, when we have any given bounded acceleration model and we want these vehicles to, the idea is that we want the vehicles to accelerate freely without slowing down, so that the density, in a sense, is low enough for them to travel at the maximum acceleration until they reach the free flow speed. So this is the bounded acceleration state with the different colors. And the idea to guarantee this minimum speed in blue is that the speed at the end of the bottlenecks is the minimum V2. And again, this V2 depends on the speed limit imposed. So this V2 is only the free flow speed or critical speed when the speed limit imposed is allowing a flow rate of the bottleneck. And this is actually what most people do, right? We want to have the maximum flow, so we're targeting for this speed limit. So the reasoning that the free flow speed needs to be reached is a good intuitive assumption. However, we don't need to reach it before the bottleneck, but after the bottleneck, or at the end of the bottleneck. Because in between, what we are assuming is that there are other fundamental diagrams, right? So in between, there can be many other fundamental diagrams. And what we are doing is we are accelerating on a standing wave. So we are moving and reducing the density in this direction from left to right. And we need to be always in a density that is lower than the density of the fundamental diagram associated to that given location. So the condition of the free flow speed, that's the last speed that we need to reach, is at the end of the bottleneck. And in between, it can be lower. And this lower speed is the equilibrium speed for the given location and density. It's the blue one. So it's not, let's say it's not it's a condition there, but it's not active because it's very far away. The only critical point is towards the end of the bottleneck. And actually, it's usually where the congestion starts, and then it builds up for the whole bottleneck, right? So.
Interesting. Thank you. We have a question in the chat here. Let me read it for you. Thanks for the interesting presentation. Here's a question from your UCI folks. In your 25th slide, number 25, the black dot in the fundamental diagram. So yeah. Let's go to that slide. The black dot on the fundamental diagram, the speed limit to prevent capacity drop, move the green dot, the speed limit in the capacity.
Yes.
Does it require the speed limit zone move to upstream?
Yes. So maybe I wasn't clear enough here, but when we put the speed limit that is lower than U3, so the black dot, the right-hand side black dot, the speed profile of bounded acceleration is the one in the right-hand side, and it can be located just upstream of the bottleneck from all the theory. But if we increase the speed limit, this location increases. So we need to further move upstream the variable speed limit zone. So that would only work if we have several gantries, or if we are using connected vehicles, where each vehicle can have its own speed profile at a given time. And we change the rule, right? Like the condition. So at the end, what we would have is the green speed profile. But from the black to the green, I didn't draw them, but you would need to have to move the speed limit zone upstream and constantly have a bounded acceleration that vehicles are accelerating earlier and earlier. So there would be many gaps there.
Hopefully that answered the question.
Yes, thanks for answering. Nice presentation. Thank you.
Thank you.
All right, excellent. Maybe we have time for one more question or comment. Very good. So if not, wait, we have a chat here. Oh, thanks for the presentation. All right, everybody. So thanks again for coming. Especially thanks, Irene, for giving this very interesting webinar. And so I will be posting this shortly on our YouTube channel from the TFT committee. There, Irene, maybe you can post a link to the presentation if people are interested. Yeah, I encourage you to go to that channel and watch the videos. All right, and our next speaker would be Eddie Wilson from Bristol, June 25th. Maybe we have somebody else in between, but if not, we'll see you there. All right, thanks everybody.
Great, thank you.
Thank you, bye-bye.